coming slides, I will be explaining about why Comcast has chosen UEFI standard for implementing their RDK bootloader, and secure boot features and its advantages, and detailed explanation about developing the secure bootloader. UEFI bootloader for RDK. Comcast looking ways to introduce more standardization to its set-top box firmware boot process. Traditionally, set-top boot architecture is based on the U-boot or proprietary. So it takes a lot of integration efforts when if you implement solutions on different SoC vendors. So to reduce complexity and interoperability between SoC vendors, the UEFI standard used to take the place of a traditional OS bootloader. And UEFI supports secure boot, and which doesn't require any hardware support other than a flash. And the UEFI standard provides a protocol interfaces for different services like HTTP, flash handling, or file handling. So using this, you can implement your bootloader and boot applications, which can be ported easily on, across the SoC vendors. So RDK, we are working on implementing RDK bootloader and DRI, that is disaster recovery image, using UEFI standard. Okay, so EDK2 is a cross-platform firmware development environment for UEFI specifications. So we are using Tiana Core EDK2 as our development environment. So these are the two links which gives a setup and build instructions for creating a flash image, firmware image for ARM KEMU and HiKey board respectively. So on top of this, we are implementing the RDK bootloader. So secure bootloader, the secure boot is designed to protect a system against a malicious code being loaded or executed in early boot process, that is before OS operating system loaded. So when you enable a secure boot in UEFI, so for every boot, the UEFI firmware try to inspect each UEFI binary image that is loaded and ensures that it is having a valid signature. So these certificates, whatever the trusted certificates in UEFI, we can store as a UEFI variables in non-volatile memory. So basically in secure boot, these are the main keys which we need to talk, like platform key. So platform key offers full control of secure boot hierarchy, and whoever holds platform key, they can update new PK platform key, or they can update KEK. So, and the KEK, it is a key exchange key. So using KEK key, you can either sign the binary images or you can update the DB. So if the KEK has a trusted certificate, using that you can update the DB. So and the DB is like whitelisting the other authorized certificate. So any keys which you are, any binary images which you signed, to authenticate that, you have to register those certificates into DB. So secure bootloader. In general, x86 machine, or in case of ARM KEMU also, we can enable secure boot using device manager UI. But in this case, we are not using UI. Programmatically, we are trying to set the platform key by which we can enable the secure boot. And once you set the platform key, you have to see the setup mode, whether it is in a user mode or not. If it is in a user mode, then it is a it is in secure boot. So once it is in a secure boot, only signed images can be executed. So to validate your signed images, you have to register your KEK as well as DB keys. So that is the basic implementation we have to do. So we started implementing RDK bootloader. So in EDK2 environment, if you want to develop a module, so you have to create a INF for that module. So which is having your source code. It is kind of makefile, I can say. So which will have your source code as well as packages, EDK2 packages which you are trying to use in your code, and PCD variables, so and global variables which you are using. So those things you have to add in your INF file, and then for enabling the secure boot. So in general, they have in UEFI they have some global variables. So those variables you can set in your program by this UEFI runtime service. They provide some set variable and get variable. Using those APIs, you can set the, to enable secure boot, you have to set the custom mode global variable that is part of a security package. So you have to set that one to secure boot mode. Once you have done that, what you have to do is you have to load platform key, a certificate from FAT file system. Say in your flash, maybe you flash your FAT file system where you can copy certificates as well as other UEFI binaries. So in our bootloader code, we are loading this platform key, and then through file system protocol, we are getting that file handle, and then the data, whatever is there, that we are updating into UEFI signature list data. So this data has to be, this data has to be set. So through set variable, once you set that, it will enable the secure boot. So you have to just validate whether the setup mode is in custom mode or user mode. So it has to be in a user mode. So after that, so for setting that, you have to give these attributes also, like UEFI variable, non-volatile, and other attributes you have to set. And the same way, we are setting other keys also, KEK and DB keys. So, and one more important thing is like ARM QEMU virtualization platform. By default, it supports a secure boot, but whereas a HiKey, it doesn't support. It is not supporting the secure boot. So we added required secure bootloader packages and other variable, drivers into their platform.dsc. So HiKey.dsc platform description file, where we added this packages and drivers to enable the secure boot. So after that, we are able to see the secure boot on on HiKey side also. So once you enable the secure boot, all your UEFI binaries or images has to be signed. So then only it can execute, only signed images can be executed. So the kernel part, so basically if in ARM kernel, in the old code, I think there is a Linux loader which will load the Linux kernel. But if you are using kernel version 4.5, it has a UEFI stub implementation which will try to load the kernel by itself. So it acts as a UEFI application. So if you are using the old kernel or something, you have to use a Linux loader application, which is available in EDK2. But if you are using kernel version 4.5, So it works as a, straightforward, it works as a UEFI application. So when you are using a UEFI application, so you have to get that image using a load image protocol, and using that protocol, you will get a file image handler. In this case, it is a kernel, so we have to pass a kernel argument. So how we are doing this is, so in UEFI, they have the EDK, they have this loader options available. So in the loader options, we are setting the kernel arguments. So what we have to see here is it is not ASCII. So the kernel arguments should be in Unicode. So you have to convert that ASCII string to Unicode and then set those arguments for load options. So with that we are able to boot Linux kernel in a secure boot mode. So this one, I'm just mentioning how to create a pair for private key and a public certificate. So the key using private key pk.key, you have to sign your binary images, I mean EFI binary images, and the corresponding certificate you have to put it in your flash or your FAT file system. So for validating the EFI images. So so this is very basic bootloader functionalities. What we are doing, just enabling the secure boot and programmatically, and then giving the kernel, I mean EFI based kernel, that means kernel 4.5 onwards, and then the kernel arguments through loader options. So with that, we are able to boot, and initramfs is very basic initramfs. With that, we are able to boot kernel in ARM-QEMU as well as on HiKey board. So still, the work is like we need to implement. So currently, we are just very basic initramfs we are loading, but the plan is we need to create a monolithic image or fit image where you will have a kernel and rootfs, everything together has to be signed, and it has to be loaded in a secure boot mode. So that is the next task. After that, we have a disaster recovery image implementation. So Comcast, they have a DRI module for supporting I mean, disaster recovery image. That means it has to be loaded, the monolithic image, the latest monolithic image has to be updated, and you have BDRI, backup DRI, different modules are there. So we are planning to implement this functionality using UEFI standard. So that's all. I think, yeah. So this is very simple bootloader we implemented using UEFI, but we face some issues like a HiKey, the EDK2. It is a somewhat old code compared to the latest EDK, whatever we have. The HiKey branch is a bit old code. So the FDT side, I mean for Linux kernel, passing the DTB. In general, you can pass a DTB as a kernel argument. So it can, but in the secure boot side, if you pass the DTB as a kernel argument, it won't allow that. So you have to update your FDT variable in EDK2, and based on, so when the kernel is booting up, it will look for this FDT variable, and based on that pointer, it will take the DTB file and it will update. So in the latest code, that part of driver like FDT driver is available in the latest EDK2, but whatever the HiKey branch we have there, that code is not available. So we have to implement, we have to see how we have to do that part. Still, we are working on that. That is the update on this work. Okay. Yeah, that's all. So, any questions? Yeah.
Curious if anybody spent any time looking at how the UEFI secure boot stuff might work in an environment that has like AB style updates. So I was curious how the UEFI secure boot process, that's, I believe, expects just that it always boots a single next partition, and so or single kernel, that sort of thing. So with something like AB updates, where you have multiple slots that might have different signatures, you know.
Okay.
Has anyone kind of been thinking about that in this work?
Can you repeat again question? I didn't understand.
A mode that some devices are using for updates
Okay.
is that they have two slots.
Okay.
And so that they can, you know, boot a new kernel or the old kernel. And so when you do an update, you only update one and move the slot pointer to,
Okay.
you know, point to the other partition. And that, you know, allows you to do rolling back to the old version if you need, or, you know, also just updating without corrupting a
Okay,
good
okay.
image. And so I was curious if that was something that anybody's kind of looked at within the
Yes.
CPI framework.
Yes. Yeah. So the DRI, the disaster recovery image, that do that only. So, but still we didn't started working on that. But DRI, so in the kernel boot, if the boot is failed, so if it will check for 10 times or something, if it is boot fail is happened, then we will go to the DRI side. The DRI, it will have in some location, it will have a monolithic image that we will take, and we'll try to boot up that. If that is also failing, then we'll go back to the backup DRI. So that way, so that implementation part is there, roadmap. Yeah. So.
And is that part of, like, is that in the UEFI standard for it? Okay.
In UEFI, you have a notion of bootloader, and you can specify, you know, attempt to do that, then that, then that, if there's a failure. And signature is orthogonal to that, right? If the signature fails, then you go as if, you know, a boot device had failed.
Yeah.
But you can't read a USB key or whatever, then you move to the next item in the list.
Okay.
But the disaster recovery scheme is implemented as a UEFI runtime application. So Comcast has specific requirements, like we'll try something 10 times, it doesn't work, then we do this. So any logic can be implemented in the UEFI runtime environment. Comcast does it a particular way, and anyone then who provides, like an OEM providing a box to Comcast, essentially, there's no need for them all to redo it. Once those applications or runtime apps are written that implement the requirements for this disaster recovery scheme, like typically like on set-top boxes, you have like a swap if a new download fails, you revert back to the old implementation. Or if there's still some other problem, then you can try to do a network download. Does Comcast have requirements for like a TFTP download or any kind of a network download?
So yeah, I think HTTPS is there, I think. Yeah. Any other questions? Yeah.
Is the HiKey UEFI port upstreamed already on it? Because you're saying it's an older version that you're using. So I guess the HiKey UEFI never got upstreamed.
So,
I just checked with Art. It is very old code, so they don't have any plans to upstream HiKey related changes. So anyway, next version of HiKey is coming, it seems. So
my sense is that it had been moved to the recent version, but maybe this is a little bit back now. And so I'm not sure. I would hope that we would get it upstream. So that's disappointing if we're not. So.
okay. Yes.
Does any part of your system require the use of EFI variables? Because EFI variables, as set from the distro and things like that, are a huge problem for HiKey at the moment. I'm just wondering if your work will contribute to solving it, or if you don't need it.
I mean, I missed.
EFI variables at the moment on the HiKey can't be stored because on a PC they get put in NOR flash, and because the operating system and the firmware share the eMMC, and the operating system is busy using the eMMC when it tries to set an EFI variable, you can't set EFI variables. It's a long-standing problem with EFI on embedded devices. And I was hoping that as embedded companies like Comcast get involved in using it, that problem would be overcome. I'm just wondering if your work is likely to contribute to solving it or not.
Yeah, as of now, we are just, it's a reference implementation. So, yeah, I mean, hope we will look into that. But we were discussing in LG that there is one more implementation using U-boot. The EFI application you can use through, even in U-boot also. So which has to take, that part still we are yet to take a decision on that. Yeah.
You just mentioned about the HiKey is not cannot support the secure boot. So does that mean you cannot verify the UEFI image by HiKey ATF? No. So what does it mean?
Though the secure boot means if you sign the images, it has to be validated and it has to be run. But when you signed or unsigned, if it, the secure boot mode has to be enabled, but that part is not supported. UEFI images are running without validating the signature, those stuff. Okay. So it supports a UEFI. So it has a UEFI firmware image through which you can run, you can launch a UEFI binaries. But it is not secure. Like signed images, if you flash it and try to launch, it won't validate anything. It will just execute that.
So that is, what do you say, HiKey doesn't support the secure boot?
Secure boot, okay. Yes, yeah.
So I had a similar question.
Yeah.
So if secure boot is not working on the HiKey and you're currently only doing this with QEMU, what other development options are available where secure boot is actually working?
So in HiKey, we enable, I mean, it's just a software. We have to just added some libraries and some packages in the HiKey.dsc file. So when you enable, when you add that, the secure boot is enabled. I mean,
So what you can't do on a HiKey is sign what ARM trusted firmware would call BL1. But you can embed the keys in BL1 that UEFI then uses further down as though they were embedded secrets. So you have the full architectural simulation of secure boot. But that first step of actually putting the first bit into RAM, we don't have the capacity on HiKey to sign.
Okay, but my question still stands because so far I got the impression that only like the enterprise kind of server-grade vendors were looking into EDK2, and I would still be interested to understand like which vendors in this home networking set-top box are actually looking in a fully implemented UEFI where those features are available.
Okay, let's go. So 96 boards is public boxes, and they're never going to ship with the security hardware to sign the first stage bootloader turned on. I believe HiKey is actually capable of doing all this in hardware, but the fuses won't be set up correctly. So, and I think you'll see the same thing across the whole of the community available boards. Nobody's ever going to make one where the secret keys are kind of known.
Sure, but that I wasn't really asking about community boards. Simply, it was like usually the thing is if there's no like base software implementation available that the vendor or an OEM can actually take from, then they're not going to ship it in other embedded devices either.
I don't know if this answers your question, but I know that in the case of Comcast, doing this reference implementation, they are currently discussing UEFI with their OEMs, and this is an effort that is, this is like a first step, but there is more interest. We see the OEMs doing their own reference implementations for Comcast. So we hope that this will create momentum for UEFI. And of course, if it is implemented in production deployments, then it will go through their, production facilities and be, true root of trust, secure type things. Does that answer your question, or? Kind of, yeah, that's what I thought.
Let me add a little bit there. Usually this kind of infrastructure is provided by the silicon vendor because the root of trust, the true root of trust has to build into the silicon in order to secure the environment from the bottom. And then doesn't really matter what the second stage of the boot is, either UEFI or U-boot. And that even that image will get signed and encrypted. Then the silicon boot ROM will decrypt it based on the root of trust key. And then you continue on the boot, the UEFI or U-boot can decrypt the subsequent secure image. So there are 3 stages of security in terms of booting.
Okay.
We can follow up separately.
Okay. Yeah, thank you. Thanks for attending the session.